All right, yeah, thanks for having me on. I'm Todd Gamblin from Lawrence Livermore National Lab. I'm the lead for the Spack project, which we'll talk about today. Spack, I think folks know on this call, I mean, I was told people would be reasonably familiar with the tool, that there are lots of dependencies that people have to manage in HPC. A simple library like MFEM that does higher order finite elements it's fairly domain specific, but you have to manage like 31 packages, 69 different dependencies for that. Machine learning libraries are even larger than that, and then there's the R and say Python ecosystems that can run upwards of 100 dependencies per package. And so if you're managing software for a unique system like a supercomputer, you may have run into the trouble of getting all of these things installed. Even proprietary codes are using lots of open source packages as well. So this is Livermore's Aries package. You can see that like these pink nodes in the graph are internal software packages. So that's the code itself. There's a whole bunch of open source and internal projects that it relies on. The orange ones are the open source ones developed at Livermore and maintained out on GitHub. And then the internal ones are like, I don't know, either things we haven't released or export controlled stuff that goes into the code. And then all the blue nodes are external open source. We're not going to go and re-implement all of the things in the open source libraries we rely on. And we couldn't. Like it's decades of work by lots of people. And so using open source allows us to leverage the work of others really effectively. But now we're in charge of ensuring that all the things fit together properly. And so in some sense, we have to manage a system that we don't know as much about because all these packages are written by other people. And so integrating that can be quite difficult. Spack is designed to simplify that problem. It automates the build and installation of scientific software. It does source and binary packaging. It's designed to provide the flexibility of, say, a regular package manager that you might have for like a language or for your Linux distro, but to provide a lot of parameterization on top of that so that you can tweak and tune the configuration for your system. So in the simplest case, you might clone Spack from github.com/spack/spack. You can install HDF5, and then you have this syntax that you can use to install things with particular versions, particular compilers. You can add options that are sort of defined by the package owner and so on. And so we're trying to provide the ease of use of mainstream tools, but with the additional flexibility needed for HPC. It will generate module files for you. So if you're using module files at your HPC center, you can actually use Spack to both install and generate modules for users to use for the packages that are installed if they don't want to go through Spack. You can create virtualenv-like environments, and this is similar to Conda as well. And then there are a bunch of DevOps features in Spack that people use for things like CI, for generating containers, for maintaining lots of dependencies for, say, application teams and so on. And then Spack supports binary packaging, like I said. It's not just a build from source system. We've actually done a lot of work on the binary packaging part of Spack. So the project has been around since I started it in 2013 to help out a grad student who was having trouble installing all her dependencies on the BlueGene-P system at Livermore. And for a few years, it was mostly internal to Livermore. And it's grown quite a bit since then. This is showing the lines of code in the actual package recipes in Spack over time, and you can see the orgs that contributed different pieces of the package ecosystem. So, I guess the main thing to notice is that at this point, Livermore, while we're still the #1 contributor to packages, mostly through kind of routine maintenance stuff and not specific package knowledge, we benefit a lot from contributions from the community. And there's over 1,400 contributors at this point to Spack from lots of different places, national labs, academia, industry, and others. And it's used around the world. This is users over 2023 for the project. It's what Google Maps would give me. I think the user counts are probably exaggerated but the monthly active user counts are like around 6,000 people a month are active on the doc site. So it's a pretty big user community. The users are from lots of different places. There are research software engineers, developers, system administrators, support staff, data scientists, computational scientists, and so on. And I think the notable thing here is really that it's the user breakdown is not biased towards any one segment of the population. It's really everyone who uses HPC. So, it's used by admins and developers for deploying for lots of people, or it's used by scientists to deploy their own code. And I'd say most of the usage is at national labs and academia at this point, but we are getting more people from cloud providers and companies using Spack. And in fact, Amazon and Google are using Spack in their HPC sort of cloud cluster offerings. So they offer a software stack through Spack that you can use on either Parallel Cluster or Google's. I guess it used to be called HPC Toolkit, and I forget what they changed the name of it to, but it's their create a cluster in the cloud tool. So again, it's for end users who just want to install and run an application. It's for application teams who manage a bunch of dependency libraries themselves. It's for developers who might want to package their own software for distribution or get more people to use their software easily. And it's for user support teams at HPC centers, which is really the original group of people that we wrote it for, but it's gotten bigger than that since then. At this point, the Spack project is the large community that I mentioned. It's a tool that is the package manager itself. It's a whole bunch of package recipes, so over 8,000 of those at this point. And then it's a lot of CI infrastructure that we maintain in the cloud and at the University of Oregon to test all the contributions that people make to the project. And so on top of this, you could think of Spack as a tool for building lots of different software stacks. So say E4S is ECP's software stack. That's the exascale computing project. I think that stands for Extreme Scale Scientific Software Stack. That's like around 100 packages that are pretty DOE specific, plus there are like 500 dependencies that are all managed as an integrated thing. They do releases, I think 2 times a year at this point. Amazon has their stack, like I mentioned. Livermore has an internal stack. There's a math library stack, visualization. Every application is essentially maintaining a stack of packages, and so on. And so you can maintain these things easily as an integrated set of packages using Spack. The CI system is just meant to show that it's its own complicated thing. We're essentially maintaining a service in Amazon on top of Kubernetes that interfaces with GitHub, sees all the pull requests coming in, farms them out to a GitLab server, and runs like I think 15 or 16 different software stacks in CI, and builds the part that changed whenever someone submits a change to a package. And so we make sure that the whole stack continues to integrate, at least in some configurations, and we actually maintain public binary caches for that. And so that's the CI is split across Amazon and some machines at the University of Oregon. They have a pretty big cluster of lots of interesting architectures, including AMD, Intel, and NVIDIA GPUs. And then Google has some runners that they contribute to the CI system as well. We recently became a Linux Foundation project, which means that we have our own legal entity. We're part of the High Performance Software Foundation. We're going to have our own technical steering committee as we get onboarded here, which will have public meetings. And so we're hoping that this allows us to make the project a bit more open. I mean, it was already pretty open. We have a call every Wednesday for people who need help. That gets advertised on our mailing list and on Slack. But we're also trying to open up the technical governance, which has historically been like a small group of people at Livermore and some outside contributors. But we're going to try to make that more public. The project is not, I mean, I guess what this means is the project is no longer owned just by Livermore. The trademark's owned by Linux Foundation. And so if we ever decided to stop maintaining it, it could continue to exist beyond that. We're not going anywhere, but the hope is that we could make it more appealing for other people to jump in and help out with development of Spack, more than we have already. Right. So if you're thinking about what Spack is, there's really 3 concepts that go into that are worth keeping in your head. The first one is that it's a syntax to describe package installations. And so HPC people want to customize things, right? So they want to provide different flags, they want to provide different options, they want to build things in special ways for their system. The first piece of Spack that we developed was a syntax for doing that. And so if you think about installing a tool, say it's called MPI leaks, in the most basic case, you would just name the tool and say, hey, Spack install that thing. You may want to specify what version you want. So we have a syntax for that. You can say add 3.3. You may want to specify what compiler to build it with. So you can say build that thing with GCC 4.7.3. You may want to specify options or inject flags into the build. And you can specify specific microarchitectures. So like we actually support names like Cascade Lake, Skylake, and so on, so that you can build specifically for the type of machine that you're running. We support generic ones too. So if you need to build for something that's portable across a range of more modern Intel processors, you could target like x86 64 v3, which is basically everything up to AVX 2, and then you can also target generics for other instruction sets and so on. And then finally, that syntax is recursive, so you can have control over your dependencies as well as the root package. So you can say MPI leaks at 3.3, but I want it with mpitch 3.2, and I want the whole thing compiled with GCC 4.9.3. So using that syntax, you can write package files that basically describe how to build a project. So if you think about a package file in Spack, there's around 8,000 of these. There's one per software project, basically. And this one is for a little mini app that does discrete ordinance transport. And essentially, what this is doing is so this is a doc string that says what it is. There's some metadata up here that says this is the homepage, this is where you can find it, the URL. And then there's all these directives at the top. And this part of the file, this sort of top part that has all the metadata, is really describing all the ways you can build the package. So it's declarative. It's saying there's 3 versions available. They have these checksums if you download them. Spack will infer the download URL from basically this URL up here, and the version. There's 2 build options. You can build with or without MPI. You can build with or without OpenMP. And then there's an optional dependency on MPI. So when MPI is enabled, we depend on some MPI implementation. And we depend on CMake 3.0 or higher. So that's a constraint on the version of CMake that you depend on. So given this, I mean, you could imagine that you could build any of these versions with any combination of the MPI and OpenMP options, and with or without these MPI dependencies and so on. You can plug in different CMake versions. And so you can see that this sort of defines all the different ways that you could build this package. Spack's job is really to take this metadata and pick a configuration for you based on what you said your requirements were. And then that gets basically passed to you, and the install method and like these CMake args methods here, they're responsible for translating the spec, which is basically what Spack picked, into build instructions. And so in this case, all it's really doing is saying like, okay, if OpenMP is enabled, then we're going to say enable OpenMP equals true. If not, it's going to be false. And if MPI is enabled, enable MPI is going to be true. Otherwise, it's false. And so the recipes are pretty simple. This is just basically saying, here's how you call CMake to build this thing with the options you asked for. This package didn't have an install method, so we had to write one. Usually you wouldn't need to do this because like most CMake builds do have an install target. But here, this just makes a directory and copies the executable into it once it's built. And Spack sort of handles the rest behind the scenes because this extends from CMake package. But really, if you want to write a package, the simplest thing to do is to write, all you really need is an install method. So you can package anything. It doesn't have to be built with CMake or AutoTools or whatever, although it is nice if it is. So the last piece, and remembering that I kind of move my slides around here, so I'm going to move this dynamically in the middle of the presentation up ahead. The last piece of Spack is the concretizer. And this is the part of Spack that does all the thinking. We discovered when we were writing this, or the need for Spack was really precipitated by people had build scripts for their projects to build on supercomputers, and they were filled with things like, hey, is MPI installed? Okay, where is it installed? Which MPI is it? Is it mpitch? Is it OpenMPI? And so on. And so the bulk of these build scripts were sort of consumed with all of this hunting around and trying to figure out exactly how to build for the current system. And that's actually an NP hard problem. And so really what Spack is doing is it's taking all of the things that the package authors told you. So all the things from the build recipe, plus stuff on the command line. So if I say Spack install HDF5 at 1.12.0 plus debug, plus other config files. So you can have like environments with their own configuration. You can have global configuration for Spack and so on. It takes all of those preferences and requirements and dumps them into a constraint solver. And we call that the concretizer. And its job is really to say, okay, given all these requirements, produce a pretty good graph that satisfies all of them, and that includes that's a complete description of how to build. And so it takes preferences and spits out complete build graphs. And so that's really what the tool's doing for you. And what that does is it takes away all of those decisions that the build script author had to make. And it handles them in a more complete way with a declarative syntax for saying, here's what the requirements and options are. On top of all of that, there is this concept of environments in Spack. So you saw that you can say like Spack install HDF5 at some version. Environments are essentially a way to deal with a bunch of specs at the same time. So this is how we build up software stacks. It's a file that looks like this. It says Spack. You can include some configuration, or you can write configuration directly in the file. There's a lot of documentation on that. And then there's a list of specs here, HDF5, libelf, and OpenMPI, that you want to build together. And you could think of this as sort of the analog of those specs on the command line. This is just in a file saying build all of these things together. We can concretize them all together and spit out a lock file that basically says, here's a reproducible description of how to build this thing. And on top of this, we have built a lot of different workflows. So there are ways to add external packages. So you can say Spack external find on the command line. It'll spit out configuration that allows you to point to software that's installed on the system that's useful for specifying like your local CUDA installation or your local MPI installation. You can build testing into this thing. So if you build a bunch of things in an environment together, you can say Spack test and it'll run the tests for all of them, make sure that they're still working. You can generate CI pipelines, which is actually how we maintain our CI system in the cloud, and it'll generate GitLab CI YAML files that define a job per build. And you can containerize things. So you can take an environment and you can say Spack containerize. It'll spit out a Docker file that basically clones Spack and builds all the stuff that you asked for in a container. And then we have some newer stuff in our binary support that I may get time to demo later, where you can basically build a whole stack and push it into an OCI registry where each package becomes a container on its own. And so that's been a pretty cool way to sort of improve our container support. There are developer workflows built on top of Spack environments. You can have a Spack.yaml like this that has my application as a spec. If you want to develop subcomponents of it or just work on them, you can say, hey, I want to work on the MFEM component of this application or the Axum component of this application. Those are two dependency packages for one of our codes. And you can say Spack develop that thing. It'll check out the directory for you, and you'll get a sort of source checkout. You can hack on that and sort of iteratively build the package with your whole environment. And so that has enabled our code teams who work on pretty complex integrated codes where there may be multiple dev teams working on different packages that have to work together over time to work across different repos and to submit pull requests to all of them and have them all integrated sort of in their cluster environment via this workflow. People have started building front ends on top of that. So the Spack develop interface is kind of simple. But there's a Spack manager tool from Sandia. The Fermilab folks came up with Spack Dev, and so they did some work. And some other folks are working on additional Spack commands to support more dev workflows. We don't really have what I would call an opinionated dev workflow yet. We're trying to build the components that people could use to make what they want. But these other projects are a bit more opinionated and sort of we're waiting and seeing which ones catch on. Before we pull all of this back into Spack, but we are pulling in basically the minimum required functionality to support external dev environments. So you can check some of these out. So the Spack has grown to the point where we needed to support a lot of conditional logic. So under ECP, we added GPU support for AMD GPUs, for more NVIDIA GPU support, and also for Intel GPUs. That required us to consolidate a lot of the build logic into our sort of package DSL. And there's a whole lot of conditional logic involved in that. So if you have a package that can be built like 3 different ways for 3 different GPUs, nobody wants to write all of the CUDA constraints and things that go along with that. So we have base packages in the Spack repo that you can extend from. So if you want to do a CUDA package, you can basically extend this one. And a lot of packages do. I think we have like 300 and something CUDA enable packages in Spack at this point, where you get basically an option for enabling or disabling CUDA. You can set the GPU architecture that you want to build for, which is basically the compute capability. And then the package encodes the relationship between different CUDA versions. So you may build with a different CUDA version on different systems, which compute capabilities they support, and also which compilers they're compatible with. So we have rules in here for GCC, Clang, and VHPC and others, so that that you need GCC 9 or higher for this CUDA version on that architecture and this CUDA version on that architecture. This is a very abbreviated version of what's actually in the CUDA package. When the project started, the concretizer was pretty simple. It was very greedy. It had a simple algorithm, and we had to grow it to support this stuff. And so what we've done is we rewrote the concretizer in something called answer set programming. And you don't have to know this as a Spack user, but essentially this is it's a programming paradigm. It's not Turing complete. It looks a lot like Prolog, but it lets us do very complicated logic solves inside the solver to handle this sort of extensive conditional logic, all the different combinatorial options for packages. It enabled us to boil the solve down into something completely declarative, where we would basically spit out a bunch of facts about the thing we were trying to resolve, and run that through the solver. It comes back with basically what it calls a stable model that says this is your solution, and we go and reconstitute the graph from there. So we don't have to do all the complicated stuff we used to do. That has been pretty effective in allowing us to implement things like reuse. So originally, Spack would basically build everything from scratch every time. If some particular hash was already installed or some particular build of a package was already installed, we would resolve the packages. We'd get a configuration hash for them, and we'd say, hey, is that installed already? This was really sensitive to option changes. And so with the new features from the concretizer, we're able to go from something like this, where I'd say like, hey, go install HDF5, and it comes back and says, okay, I'm going to build the whole thing from scratch, to something like this, where it says, oh, I could actually reuse 16 of the packages that you already have installed to get what you want, with not a lot of downside. So you can see like over here, it was saying, oh, well, I must use the latest version of CMake 3.21.4. And over here it said, well, you have 3.21.1 installed, and that seems good enough for what you're trying to build. So I'm not going to go and reinstall that. And so we get both reproducibility in that we are building a very specific configuration of a package that you can then rebuild from one of these lock files, and also we're able to reuse the things that are already installed without causing users to have like 6 copies of Python on their system. We've been trying to deal with more complexity in the Python ecosystem recently. There are situations like this one where you've got diamond dependencies between packages, and NumPy requires a really old version of Python, and PyGEvent used to work with, or NumPy requires a really old version of Cython, and other packages like say PyGEvent could build with that version, but only at a very old version of their own. So like the latest version of PyGEvent is like version 30 something. And we have to downgrade this package unnecessarily to be compatible with essentially the same version of Cython as NumPy. We have tweaked the solver so that it's a bit smarter about this, where essentially it says the things that you need at runtime, we're going to unify. And so, if you have a link dependency, or if there's some Python package you need to use while your application is running, we'll unify all that and allow one version of each of those things. But we are now smart enough to split out build dependencies, so that essentially GEvent can build with the version of Cython it wants, NumPy can build with the version of Cython it wants, and everyone's happy. We can use a current version of GEvent and a current version of NumPy. They just use different versions. This is actually pretty complicated to implement, so the whole ASP transition has enabled us to do that better. Background is because people are doing stuff in the yard. I hope that's not. Can people hear that? No. Let me close the. All right, hopefully they'll go away. Okay, hopefully that's better.
Yes.
All right. So Spack version 0.22 was released in May. We're doing a lot of work right now to model compilers better. Essentially, we want to do that for 2 reasons. One is people want to do compiler interop. They want to be able to use multiple compilers together in the same environment. And also, the runtime libraries of compilers are really critical for enabling binaries to install well. And so we have done a lot of work modeling the runtime libraries like libstd C++ and so on in GCC, in the Intel compilers, and Clang is TBD, but we're going to do that as well. What that essentially means is that where Spack used to represent these things as just this node was built with GCC at this version, now we model the compiler as a build dependency, and it actually can say what runtime libraries should be added to the things that are built with it. And so we have things like libstd C++ or GCC's runtime in the graph. And what that looks like, just to give it sort of a preview, is like compiler maintainers can go implement packages like this that say, hey, if you build with me, you need to add a GCC runtime node to the graph. And that one, that's a link dependency on the thing that builds with me. And you can also add some version constraints on that and so on. We have what I consider a pretty compact syntax for doing this. and it allows us to say build packages that we can go and put in a binary cache and then install, say, something built with a newer version of GCC than what the system supports on an older system. And so it makes the binary support in Spack a lot more robust. It allows us to package the runtime libraries themselves, and it lets us really understand compatibility between compilers. So that's something we've been working on. It also simplifies the way that packages are dealing with languages. So whereas before we just kind of assumed that everything had a C and a C++ and a Fortran compiler, which is not really true for most Python packages. Now only the packages that need those things depend on the language, and then basically we swap in a compiler for that dependency when we build this thing. And so this ends up being a pretty nice feature because it's much better for supporting mixed languages. So in the past, we've had to kind of lie to Spack to say like, okay, this C++ compiler is Clang, but oh, by the way, we're using Gfortran for the Fortran compiler. Now, essentially, we model each of those as independent dependencies, and we can package the runtimes for them independently and do better binary distribution around them. We've started modeling libc as well. So with this, we're sort of going all the way down to the lowest level of the stack before you get to the kernel. And what that means is that the binary packages in Spack won't be quite as prickly. We previously would tag every node with a specific OS distro that it was built with, which was really just a proxy for libc. And now that we're doing this, what that means is that we can basically look at the version of libc and say, okay, this one will work on this system because the libc version is, say, older than what you have on the system. So we can build things in a binary cache with, say, an old version of libc, like all the Python wheel people do, and produce Spack binary packages that are portable. And so the goal is really to make it so that eventually we will have binaries on by default in Spack. If you try to install something complicated, most of the lower level dependencies would come from binaries that we have built, in an optimized way in a build cache, but you would still be building like your top level numerical stuff that you want to run on the HPC system from source. And so we're trying to get a very seamless integration between binary packaging and source builds. So that's in the current version of Spack. It works way better than what we had before because you can be on essentially any modern OS and install from our developed build cache pretty well and get hits. And so when you don't have to build from source, this takes way less time. And hopefully people will not spend nearly as much time fighting with source builds. So the roadmap for this year is right now we're sort of in a crunch to finish compiler dependencies to get that. I mean, that feature is in. We're modeling the runtimes. We're trying to make the compilers into nodes right now, and we're trying to target that for our supercomputing release in November. We'll see if we hit it. We're pretty close, but it's a really big feature, and it's probably the biggest change we've made to Spack since we rewrote the whole solver. We're trying to harden the public build caches and make it so that they are more broadly compatible, that you can more likely get binary packages. And we're trying to enable bare metal installations for things like MPI binaries, CUDA binaries, and ROCm installations, where you're really depending on the ABI of a package from the system. That's always been hard with MPI, but we have a model where we think we can build with, say, MPitch in the cloud or MPitch and OpenMPI, and then install binaries for those things on systems that are compatible with whatever the system supports. So we're working on that. I think this is more of a next year kind of feature. We'd like to have the build cache on by default so that binaries get installed automatically. We're not quite there yet, but we're getting there. And I think this is really going to make it a much more pleasant tool to use because you won't have to build the whole world from source. And then finally, we're working on simplifying our maintenance of the Python ecosystem because at the moment we have like 3,000 Python packages in Spack. And that's becoming increasingly complex. So we've built some tools to auto-generate Python package descriptions from PyPI, and I think we may shift over to having most of the Python ecosystem maintained automatically, and where we would only have humans working on the Python packages that require like native builds that are tuned for particular systems. So we'd still be doing normal Spack packages for those. So people have asked, when we would go to Spack version 1.0. We're at like 0.23 or 0.22 right now, 23 in November. The big things that we've wanted for version 1.0, and note that like the fact that we're not at 1.0 doesn't mean that Spack is like alpha quality or something. We maintain backward compatibility as best we can. from release to release. But we do have some major features like the compiler dependencies that we want to get in there before we go to 1.0. So we've wanted the new solver that supports all this GPU logic. We wanted production CI where we're building binaries in the cloud. We want compilers as dependencies, which is almost done, and this build cache hardening. And then I think the very last thing that we would do before 1.0 is we would split the packages out from the main repo. So the two are coupled right now, where if you get a particular Spack version, it has a particular package repository that comes with it. We want to make that much more pluggable so that you could much more easily guarantee that one package repo is going to work with basically any version of Spack. And so we want to minimize the API there, pull it out. And once that's done, I think we will be able to have a 1.0 release. So we're thinking maybe June. So anyway, that's sort of the overview. You can join slack.spack.io if you want to talk to other Spack users. There's about 3,000 people on there working on the tool. And there is a tutorial which we'll be giving at SC, and which we also recently gave online. So there's if you go to spacktutorial.rtfd.io, the latest version is on there. You can actually do it anytime. Like the exercises are there, and I'll show that in just a second. So and also we have videos from the recent online tutorial we gave. So I'm going to have those posted on the tutorial site pretty soon. So if you keep checking this website, they should appear, and you can actually watch the whole online tutorial that we gave a few weeks ago if you want to. So I guess with that, any questions on this stuff before I go on to maybe some demos, or I can either show what people want to see, or I have some other things I could demo in the meantime. So yeah, any questions?
Yeah, thanks. So we have one question here. What happens when you have a lot of different versions of a package installed? What's the recommended best practice to clean up old version without affecting user job submission scripts?
Don't remove them if you don't want to affect user job submission scripts. I would say you can run Spack GC to garbage collect things that are no longer used by stuff that you're maintaining. But I mean, most of the sites that are deploying Spack for users will have like different releases of their own software stack. So they'll pick, a Spack version, they'll deploy some software, they'll say, here's the stack for now. They'll use that for a while, and they may add to it, but they typically don't remove things. So unless you know that users are not relying on something, then I would say like I wouldn't remove it, because that you don't know what the users might be using in their job submission scripts. And then typically sites will remove older versions as they do new releases, and they'll just say, okay, we're not supporting that one anymore. You'll have to transition at this point, and then the users know when things are happening.
All right. Yeah, that's more or less our approach. Just not remove anything and just keep growing the file system. It's not that huge of a hit on a space compared to just the build, the build side or the size of the build packages. All right. Another question. What are you doing with Anaconda/Conda context licensing changes? So are you guys to any extent affected by Anaconda? Maybe I rephrase that question.
I mean, we don't use Conda, so no. I would say. I'd say you could consider using Spack instead of Anaconda if you were concerned about the license changes, although there's Conda Forge too, right? So yeah, I don't think we're really affected by that. We do have a mini Conda package, and I suppose it uses the default Anaconda repo as the default, but we're just packaging what mini Conda puts out there. I personally don't like it that mini Conda makes the default, or that they make the default repo the non-free one, which I thought was a bit of a bait and switch. But I would say either if you really want to stick with the Conda ecosystem, then consider switching to Conda Forge, or and look at some of the alternatives to Conda. So there's Mamba is one that defaults to Conda Forge and is faster than the Conda solver, and there's also Pixie from Prefix Dev. But yeah, none of that is really related to Spack.
Yeah. So now we have probably the usual question: how does Spack compare with EasyBuild?
Yeah, so I'd say the big difference between Spack, well, so there's a lot of differences between Spack and EasyBuild. EasyBuild doesn't support binary packaging, so that's one thing. EasyBuild, if you think of what Spack's doing for you, like with these package recipes, right? You could think of EasyBuild as like, I would have to write an easy config for every single one of these versions and duplicate a bunch of code. And so, if I'm writing EasyBuild recipes, then I would have version 1.2.3 has MPI enabled. It's not an option. And I would have, OpenMP enabled or disabled all in one config file. And if I want a different config, I go and write another config file. And if I want a different config, I go and write another config file. And so with Spack, what you're getting is the solver that puts all of that stuff together, which EasyBuild doesn't have either, right? Like, so you're getting this whole concretization process, and the dev workflow is built on top of environments with Spack, whereas EasyBuild doesn't have any of that. It's only building from source, and it's only building very specific human-maintained installation scripts.
Yeah, great, thanks. Let's see. Do you have any insight using Spack to deliver a software stack on highly heterogeneous system, specifically heterogeneous in terms of available processor types and generations? That's probably very common around here. So, yeah.
Well, I guess so like are you saying like you have a system that has different generations of Intel processors?
Yeah, I would say microarchitectures. So you have different microarchitectures, right?
Yeah, so I mean, Spack has, so there's this library called ArchSpec that Spack uses that we also wrote, we spun out. So you can go to here, so go to github.com/ArchSpec. And actually Conda's using this library now, which is kind of cool. I noticed that they pulled it into both Conda and to Pixie over in the Conda ecosystem to deal with architecture compatibility. This is really the library that provides all of those compatibility rules between different microarchitectures. And so there's a paper linked from here, but most of the smarts of ArchSpec are in this JSON file that all of these tools use internally. And like you can see in here, like if I have Cascade Lake, right? It says it's from Skylake AVX 512. It has all these features in it. And these are the compiler versions that support that architecture. So Spack knows about all of those target microarchitectures. And in fact, like if I go, over here on the Spack command line, so I can just do a demo. I'm gonna clone it. Go in here. I guess I should have done a shallow clone because it takes forever these days.
Yeah, maybe I'll just add one other thing we do is that we serve different module files, right, for different microarch builds. And inside of the module file, you have a logic. If you are on that particular arc, which we use your tool to figure out what microarch we're on, then add this path of node modules to your module path so that you have those particular microarch builds added to the module path.
Yeah. So if I run Spack Arch known targets, it'll spit out this big list of architectures it knows about, right? And so you can see down here that here's all the Intel ones. You can have module file directories separated by these different architectures if you want to. And a lot of sites will say, build for very specific architectures for the clusters that they have if they only have a few. So like if you have like, I don't know, an Ice Lake cluster or a Cascade Lake cluster and so on, you can pick, you can have different stacks that build for different architectures and have different versions of the code, right? And you may want to do that because like the newer Intel chips have, nice vector instructions for newer versions. But there's also these generic architectures up here. So you can see x86-64, x86-64, v2, v3, v4. This is essentially SSE plus AVX2 plus, that's it. And then x86-64 v4 is all of that plus AVX 512. And so if you have, say, older machines that don't support AVX 512, you can build x86-64 v3 binaries that are pretty broadly compatible and use those on the systems that don't have it, like the older AMD chips and so on, and older Intel chips. And then if you have newer machines, x86-64 v4 is compatible with Skylake AVX 512 and on, and it's also compatible with Genoa, so like the newer the AMD chips that have like so Genoa is Zen 4 that have AVX 512. And so like if you need to be compatible across Intel and AMD systems, I would recommend using these two. And then you could have basically a smaller set of independent builds for the generic architectures that are still optimized, right? Because they have the vector instructions, but they're not they don't have the very, very specific instructions for the newer Intel generations. Does that make sense?
Yeah, and the V2 is just AVX, right? Not AVX2.
I'm not even sure if I forget if it includes AVX or just, I think it's SSE3, but it may have AVX
That
on
might
it.
be even better. We are actually running up to Westmere CPU still on our cluster, so they are like they don't even have AVX. So yeah.
Yeah. Oh yeah. If you're still there, then it is V2. I would just, yeah, for those builds.
Yeah, but it's good to know that you can look into these micro architectures JSON file, and we can pull it out of that.
Yeah, these are the features that these are the new ones that it supports. So it's SSE, SSE2, SSE3.
Oh, yeah, it doesn't even have AVX. Okay, so
yeah.
Great. We are kind of getting short on time, but we have a couple more questions. Maybe we can still answer those. The first one is, what compilers do you support?
Oh gosh. Well, let's see. So we don't know if we have a list. We have a bunch. Maybe I have a way to query that, but yeah. So I mean, AOCC, which is like AMD's optimizing CPU compiler, Clang on Macs, ARM compilers, Cray compilers, Clang, Fujitsu compilers, GCC, Intel, MSVC on Windows, NAG, Fortran compiler, NVHPC, OneAPI, PGI. Well, yeah, this is getting long in the tooth, right? Like you should switch from PGI to NVHPC and Intel to OneAPI at this point. Rock'em CC and XL. So I mean, is there one on there that you want that we don't support?
Yeah, it's pretty much comprehensive list, I would guess.
Yeah.
Also, I would probably support only a handful of those. So, all right, and then we have one last question. We have a user here who they run pretty mixed versions of OS. So CentOS 6 and 7 actually still on 10 levels down on Slurm. Can we still use install Spack?
Yeah, you can. You can either split on. You can have a Spack. You can have a stack for CentOS 6 and a stack for CentOS 7. Although I mean, CentOS 6 is getting really old at this point, right? Like CentOS 7 even is end of life. Like what are you running CentOS 6 for?
Yeah, I would be a little worried about that.
Yeah, I don't even think you get support for that anymore.
Right, but purely legacy reason.
Yeah.
Okay. Yeah, I mean, sure, you can still use Spack to install for that. And you can still register the older compilers and still build stuff. So you could either have two stacks that are built for those two, or I mean, you should be able to run CentOS 6 libc stuff on CentOS 7. So you could have one stack as long as you build it all on the old system. Although that's going to really limit what you can build. There's no restriction though on what Spack will allow you to install. Like you can have builds for basically arbitrary combinations of things installed together, and you can generate separate module trees for them, which is what I would do.
Yeah, Carl, there's another question on this. To elaborate on containers, which actually I would probably put a plug in if you want to support all OS. It makes more sense probably to stick it in a container rather than running it on a host.
If you can find a base image for CentOS 6, which is like, I don't know if they even have that up there anymore.
Right. Yeah, so can you, I don't know if you really have much more time, couple more, maybe elaborate on containers and Spack in the next 2 minutes or something, if you can do that.
Yeah, sure. So, I mean, I guess like we have this concept of an environment, right? And it's not an environment like you would know from Python. You can say Spack env create, say, I don't know, my env. And if I edit that thing, I guess it's going to be slow for a second because I'm on this AWS instance. I can basically put, a list of things to install in my environment. I'm going to try to like skip to the interesting part of this. So like if I wanted to install like Tickle and Trillinos in an environment, I would make an environment file that looks like this, and there's command line tools for it. So check out the environments tutorial. For any environment, you can run Spack containerize and get a Docker file spit out that will go and turn that environment into a container image. And it'll also do the recipe will do a multi-stage build, so it'll basically strip out all the build dependencies before it makes the final container image. So that's one way people do containers. Perhaps the more interesting one is if you go to github.com/spack/spack or /spack, actually just Spack. There is this setup Spack and GitHub Actions build cache. We've had binary support for a while where we can put binaries in an S3 bucket. But recently we added this capability to have OCI registry build caches. And so what that means is, like, if you look at how this is structured, this is the GitHub packages registry, right? Which is an OCI registry. You can build your whole environment, and like this particular one, let's see if I can if I can find the environment that's set up here for this sort of, yeah. Here's an environment that builds sort of a basic DevTools stack, right? It's building AutoConf, AutoMate, Bison, and so on, all of these things for GCC 9, and you could add more compilers in there. This is a matrix. It just says build the Cartesian product of two things. That basically generates all of those packages, and then you can push them into a GitHub packages registry. So that's what I was showing before. So if I go back to here and look at the registry, all of those different packages are actually pushed into this container registry as tags. And so you can use that either to install them locally. So you can pull them straight out of the container registry as like binary blobs and install them on your local file system. Or if you push to this thing with and you specify a base image, each of these things is a runnable container image. So you can basically build anything in Spack, push it to an OCI registry and run it as a container image. So like you could run an image with FFTW installed in it and in your path very easily. So this is the new way that we're sort of pushing people to use containers, because it does separate the packages out over different layers. It enables you to get more reuse across layers and from different builds. And it's just an easy way to not have to set up like your own directory on a file system or an S3 bucket to create the binary cache. So I don't know if that makes sense to folks, but that is covered in the tutorial over here. So there's a binary caches tutorial where it takes you through how to build a Spack environment, push it to GitHub, and then reuse packages from a build cache that looks like this one. And it shows how to run them each as a container as well. So let us know if you try it out and have questions.
Todd, thank you so much. We are at time, and I'm sure folks have to get to 2 o'clock calls or move on, but we really appreciate your time today. It was great. Thanks for the short notice jumping on this call. I did notice that you are going to be at the Oklahoma Supercomputing Symposium. Are you speaking at that as well?
Yeah, they have me giving a talk there as well.
Great. Well, if folks want more, they can see that on September 25th. I put the link in the chat for that event if folks want to jump on that call. And next month is celebrating Cybersecurity Awareness Month. So we're gonna, if folks have ideas of what they would like to discuss in the researcher-facing track for that month, I'm still developing the call with the steering committee. So if you have ideas, please reach out to me. November, we will have Globus here for the November call. And again, thank you all for being here. Appreciate that. And thanks to the steering committee for your help today. And we will get this recording compiled and posted. Thanks, everybody.